let's see. I wanted to show you something. So we had seen Raoult's law, Henry's law, right? दिख रहा है क्या ये समरी?
नहीं दिख रहा सर, नहीं दिख रहा.
नहीं दिख रहा है. लेट मी सी. अभी दिख रहा है? Can you see this now?
Yes sir, now it is.
Yes, sir.
Okay. So I'm using OneNote, Microsoft OneNote now, and these notes are made in Microsoft OneNote. So if I look at, let's see, just a summary of what we saw. This was Raoult's law, right? Pi bar is equal to xi Pis. बराबर है? याद है? And this was Henry's law. Fi bar is equal to xi Ki. ठीक है? And we said that we can define ideal solution in terms of Raoult's law or Henry's law. Raoult's law is pure liquid at system pressure. So gamma I reduces to 1 as composition approaches almost pure solution, pure solvent, sorry. And Henry's law was for dilute solutions. And activity coefficient, which is a measure of deviation from ideal solution, approaches 1 as composition approaches 1 for solvent. This is Raoult's law. You can say this is Raoult's law. I didn't share OneNote, is it? Let me share OneNote. Can you see this?
Yes, sir.
Okay. So this was Raoult's law, which we said was Pi bar equal to gamma I xi Pis, right? We introduced gamma I to essentially show that for non-ideal solutions, we can use this thing, right? This is a correction for non-ideal solutions. If it is ideal solutions, it becomes gamma I equal to 1 and it reduces to, this is Raoult's law, xi Pis. Similarly, there was Henry's law equation. Fi bar is equal to gamma I prime xi Ki. The gamma I prime again was to show the effect of non-ideal solutions, non-ideality. And for ideal solutions, again gamma I prime becomes equal to 1 and we get this Henry's law. Okay. So now if we look at this one, can you see this figure 7.4?
Yes sir.
Okay. So in this case, if we draw Fi bar or partial pressure versus composition in the liquid phase, we'll get something like this curve. The solid line is a curve for actual data, right? So if you draw a tangent at xi equal to 0, you get this one, this equation, this line, dotted line. And if you draw tangent at xi equal to 1, we get this dotted line, dashed line, right? So this one, when xi equal to 1, almost 1, this tangent is essentially representing Raoult's law or Lewis-Randall rule. That is, what you get is fi here for your solution. This is gamma I equal to 1. And for this one, we get essentially ki here for dilute solution, because this is xi equal to 0 here, almost 0. We are talking about Henry's law, which is applicable at for dilute solutions here at this end of the spectrum, and Lewis-Randall rule or Raoult's law is applicable at this end of the spectrum. So that's how we use both laws. For one for dilute solutions, one is for almost pure solvent. Okay? Any doubts, questions on this? How it is represented? Okay, so if you understood this, then there are some problems, solved problems in the book, which actually calculates the Henry's law constant. It's very simple. I'm not going to repeat it here. You can see it. You can solve it at home because we are running late. And these are solved problems. They are very simple problems. You can see 7.10. Determine Henry's law constants. You can see it's actually tangent निकाल के किया है. Very simple. I've just explained किया हुआ. You can check it out. Even 7.11. Data दिया है. अपने को निकालने का है Henry's law constant. And this is by this only. I'll show you the graph. ग्राफ प्लॉट करने का और टेंजेंट निकालने का.
बारह तो है हमारे बैच का.
ठीक है. So you can check it out. These are solved problems which are very simple, and they are very well explained in the book. इसने यहाँ पर किया है, प्रॉब्लम सॉल्व किया है, डेटा ड्रॉ किया है, he has drawn the tangent and find out Henry's law, Raoult's law. PIS वगैरह निकाला है इसने. ठीक है, कोई डाउट होगा तो you can ask me, then we can go through that.
सर वो ग्राफ कैसे प्लॉट किया, वो एक बार फिर से रिपीट कर दो ना, वो समझा नहीं.
दिया है ना, XB वर्सेस यहाँ पर ये एक्चुअली ये जो बुक में आपको नहीं मिलेगा, ये एक्चुअली ये है, I'll tell you what it is. PA bar, this partial pressure of A है ये PA bar, and this is PB bar. ये composition of component B है. It's acetone chloroform system. दिख रहा है example 7.11?
हाँ सर.
Right. So this is given, composition of chloroform is given. B is chloroform and A is acetone. So 0.2, 0.4, 0.6, 0.81, and this is PA bar. यहाँ पर नहीं आया book scanned version में. Actually it is partial pressure of A, and this is partial pressure of B. So what you have to do is confirm that the mixture conforms to Raoult's law for the component present in excess. Excess में जो भी component रहेगा उसके लिए Raoult's law applicable है, and Henry's law is applicable for the minor component or dilute solution, right? And we have determined the Henry's law constants. So what is done is partial pressures are plotted against mole fraction of A. ये B दिया है, so what will be XA? It's a binary system, right? If XB is 0, what is XA?
1.
1. So you can find out what is the value of XA from this XB, and you can plot this graph. Graph भी दिया है इसने. So he is plotting PI bar versus XA. जो डेटा दिया वो प्लॉट किया उसने. And what is happening is you get two curves. One is for PA bar, one is for PB bar, right? ये है ना, ये PA bar है और ये PB bar है. तो दो कर्व मिलेगा हमारे को, एक कर्व इसके लिए मिलेगा और एक कर्व इसके लिए मिलेगा, right? So that is shown here, two curves, right? So when we look at this curve, suppose this is for A, and we draw tangent at XA equal to 1, acetone है, so this is actually following Raoult's law. And if you look at this curve जो B के लिए है, xb equal to xa equal to 0 means xb equal to 1, right? So this is pure b, right? तो यहाँ पर जो टेंजेंट रहेगा it will be following what you call Raoult's law for chloroform. This is Raoult's law for acetone and this is Raoult's law for chloroform. Similarly, if you draw tangent at this one xa equal to 1, that means xb equal to कितना हो जाएगा? When xa equal to 1, xb is equal to क्या हो जाएगा? 0, right? So that means this is very dilute chloroform. B is chloroform. That means this is Henry's law for chloroform. यहाँ पर tangent जो draw करेंगे. Similarly, यहाँ पर ये A के जो curve है उसको हम tangent draw करेंगे. तो this is xb equal to 1. No, sorry, xa equal to 1. Xa equal to 0 means xb equal to 1, right? तो दिस इज ये बी के लिए हेनरीज लॉ हो जाएगा, सॉरी ए के लिए हेनरीज लॉ हो जाएगा. ए इज 0 ना, एक्स इक्वल टू 1 है, एक्स इक्वल टू 0. एक्स इक्वल टू 0 मीन्स हेनरीज लॉ फॉर एसीटोन. एसीटोन इज ए, राइट? तो क्या हो जाएगा व्हेन वी टेक दिस वैल्यू, जो हमारा इक्वेशन था, इक्वेशन क्या था? इक्वेशन हमने देखा, राइट? पी आई बार इज इक्वल टू एक्स आई पी आई, राइट? लेट्स रिमेंबर दैट. पी ए बार इज इक्वल टू एक्स से पी एस, राइट? तो पी ए बार जो हमारा दिया है, ये दिया, राइट? ये पी ए बार है, ये वाई वैल्यू. तो दैट इज एट एक्स इक्वल टू 1, दिस इज पी एस. समझ में आ रहा है? इक्वेशन क्या है अपना? पी ए बार इज इक्वल टू एक्स ए इंटू पी एस.
Yes, sir.
राइट? सो एट एक्स इक्वल टू 1, पी ए बार इज इक्वल टू पी एस, बराबर. सो दिस वाई एक्सेस में जो मिलेगा हमारे को, दैट इज इक्वल टू पी एस. सिमिलरली यहाँ पर जो रहेगा एक्स बी इक्वल टू 1 रहेगा यहाँ पर, राइट? एट एक्स इक्वल टू 0. तो एक्स बी इक्वल टू 1 पर दिस पी ए बार इज इक्वल टू नथिंग बट पी बी एस. एंड सिमिलरली इफ यू लुक एट हेनरीज लॉ कांस्टेंट, हेनरीज लॉ में क्या हो जाएगा? पी ए बार इज इक्वल टू एक्स आई इंटू के. पी ए बार इज इक्वल टू एक्स आई इंटू के, राइट? तो एक्स आई इज इक्वल टू 0 पर दिस इंटरसेप्ट इज इक्वल टू के. सिमिलर दिस इज गोइंग टू बी के बी यहाँ पर इस साइड में. So from the graph you can find out the saturation pressure of A, saturation pressure of B, Henry's law constant of A, Henry's law constant of B. Everything you can get from the graph. And if you really see, data से ही निकाल सकते हो आप. When xb equal to 1, right? This is pure B, right? Pure B बोला तो ये PB बार है, so this is your PBS 0.386. समझा गया?
हाँ सर.
Right? When xb equal to 0, that means xa equal to 1. xa equal to 1 means pure A. Pure A means this PA bar is equal to PS. So PAS, PBS you can directly get from this data. But Henry's law constant के लिए आपको ग्राफ ड्रॉ करना पड़ेगा और टेंजेंट निकालना पड़ेगा. टेंजेंट निकाला तो फिर जो इंटरसेप्ट रहेगा that will give you KA, Henry's law constant for A and Henry's law constant for B. पी ए बार इक्वल ये निकाला है, पी एस एंड पी बी एस एंड हेनरीज लॉ कांस्टेंट निकाला है इसने. एसेंशियली इट इज जस्ट ग्राफिकल वे ऑफ फाइंडिंग आउट के एंड के बी. दिस इज के एंड दिस इज के बी. एक्चुअली यू हैव टू ड्रॉ द ग्राफ एंड फाइंड आउट, सी व्हाट हाउ इट वर्क्स आउट. बट यहाँ पर बहुत अच्छे से एक्सप्लेन किया, यू कैन चेक इट आउट. ठीक है? Any questions on that? Okay, if there are no questions, let's move forward and see the next topic. Next topic is Gibbs-Duhem equation. Now we have, how did we start? We started with ideal gas, right? That was our starting point that which we did in phase CET 1. Then he defined equations for non-ideal equations, right? Peng Robinson, SRK, वगैरह वगैरह वगैरह. Similarly, what we have done is we have defined ideal solution for liquids. That was for gases. Ideal gases for gases. Now we have to see liquids. Liquids कैसे handle करने का? There are no equations available for equation of state for liquids. So we have to use some other equations, and that's how we defined ideal solutions, where the components mix without change in volume. And then we introduce the concept of activity coefficient to say that, okay, because of non-ideality, the what you call Raoult's law, or rather Raoult's law or Lewis-Randall rule is going to change, and we have to correct it for non-ideality, and we introduce the concept of activity. बराबर, वो हमने लास्ट टाइम किया था. That was how we defined activity, right? ये हेनरीज लॉ में एक्टिविटी डाला था हमने to account for non-ideality, and for Raoult's law we had similarly done gamma I to account for non-ideality, right? So now we see when we have gamma I, how are they related? How is gamma 1 related to gamma 2? They are not independent. So there is a correlation between gamma 1 and gamma 2. They are related to each other, and that's what we are going to find out by Gibbs-Duhem equation. So what it says is how the partial molar properties change with composition at constant temperature and pressure. दिख रहा है आपको Gibbs-Duhem equation? Can you see Gibbs-Duhem equation?
यस सर.
ओके. कभी प्रॉब्लम आया नहीं दिखता हो, मेरा आवाज नहीं आता मेरे को, somebody should call me. आप मैसेज करते हो, मैसेज शायद मैं नहीं देखता हूँ व्हाट्सएप. So somebody can call me if there is a problem. ठीक है. So we have seen this before. Total property of any solution is equal to nothing but summation of Ni into Mi bar. हमने देखा था partial molar properties, right? This is the definition of MT, total property based on partial molar property. Mi bar is partial molar property. So if we take the total derivative of this, dmt is equal to summation of Ni dmi bar plus summation of Mi bar into dni, right? And we know that total property, any property, it can be volume, it can be Gibbs free energy, it can be anything. So MT is equal to a function of temperature, pressure, and number of moles of each component. So if you take dmt, total derivative, what you get is mt by P at constant temperature and composition into dP plus mt by T at constant pressure into dt. This should be n here. Plus mt by n1 at constant temperature, pressure, n2 into dn1, like that, up to mt by ni at constant temperature, pressure, constant nj, where j is not equal to I, into dni. So at constant temperature and pressure, this term will become 0, this term will become 0, and this equation 2 will become dmt is equal to, this is nothing but m1 bar, partial molar property by definition, into dn1 plus m2 bar into dn2 plus mi bar into dni, etc., etc., right? So we can write this as dmt is equal to nothing but summation of mi bar into dni. Okay? So if you compare equation 1 with equation 3, right? Left hand side is same, dmt, so right hand side has to be equal, right? And we have summation of mi dni bar on both. So this term, summation of ni dmi, has to be equal to 0, right? Because right hand side has two terms in equation 1 and one term in equation 3. So this term, summation of ni dmi, has to be equal to 0. dmi bar, sorry. Summation of ni dmi bar has to be equal to 0. And this is what is called Gibbs-Duhem equation. समझ में आया? Compare equation 1 and 3. Left hand side is same, so right hand side has to be equal. And right hand side में यहाँ पर equation 1 में 2 टर्म है, equation 3 में 1 टर्म है. ये दोनों टर्म सेम है, 1 and 3 का. So the other term of equation 1 has to be equal to 0. So that is Gibbs to Hem equation. Okay. So if we write this for Gibbs free energy, partial molar Gibbs free energy is nothing but chemical potential mu I. So we can write this for chemical potential summation of Ni d mu I equal to 0. So instead of mi bar, we are writing mu I. If we divide by total number of moles, then what we'll get is summation of xi or mole fraction into d mu I equal to 0. So these are various forms of Gibbs Duhem equation. This is one form, this is another form, this is another form. There you'll see many forms of Gibbs Duhem equation. And sometimes exam में आता है कि derive Gibbs Duhem equation, all forms of Gibbs Duhem equation. So you have to derive all these things. ठीक है? Any doubts, questions on equation 5 and 6? Okay. So what are the other forms of Gibbs Duhem equation? So if you consider a binary system, you can write this equation, equation 6 as x1 d mu1 plus x2 d mu2 equal to 0. From where we get x1 d mu1 is equal to minus x2 d mu2. And we know that for a binary system, x1 plus x2 equal to 0. So dx1 plus dx2 equal to 0. That means dx1 is equal to minus dx2. So we divide equation 7 by dx1. Now because it is x1, x2, we will take partial derivatives, not total. So we get x1 dabba mu1 by dabba x1 is equal to, because this dx1 is equal to minus dx2, x1 d mu1 dabba mu1 by dabba x1 equal to minus x2 dabba mu2 by dabba x1. And if we take dx1 equal to minus dx2, what we'll get is x1 dabba mu1 by dabba x1 is equal to plus x2 dabba mu2 by dabba x2. We replace this x1 with x2. So this is another form of Gibbs Duhem equation. So we see that what you call chemical potential or partial molar Gibbs energy of component 1 is related to partial molar chemical Gibbs energy or chemical potential of component 2. They are not independent of each other. They are related. If this changes, this will change. Just like x1 changes, x2 will change, right? If it is binary system. So similarly, mu1 changes, mu2 has to change. It's not independent of each other. Okay, any questions on question 8? Okay, so let's see another form of this equation now. We have defined d mu I is equal to RT dln Fi by definition, right? So substitute 9 and 8. If you substitute 9 and 8, what we'll get is x1 RT will cancel from both the sides, left hand side, right hand side. What you get is dabba ln F1 bar by dabba x1 is equal to x2 dabba ln F2, यहाँ पर बार रहना चाहिए, by dabba x2. ठीक है? Any questions on equation 10? Okay. Then we have defined activity as Fi bar by Fi0, right? This is for pure component, this is for component 1 in solution or I in solution. So substitute 11 and 10. What we'll get is x1 dabba ln instead of F1 bar, what we'll get A1 into F10 by dabba x1 equal to x2 dabba ln again A2 into F20 instead of F2 bar by dabba x2. And we know that fugacity in standard state is equal to fugacity of pure component, that is Fi0, is independent of composition. Right? It does not depend on composition because it's pure component. There is no composition. Composition is 1. Therefore, dabba ln Fi0 by dabba x1 is equal to 0. It's not a function of composition. So substitute 13 and 12. what you get is from 12, you can expand it. It is nothing but x1 double ln a1 by double x1 plus x1 double ln f1 0 आना चाहिए by double x1 is equal to double ln f2 0 by double x2 plus double ln a2 by double x2. So this is 0 है, ये term 0 है because it does not depend on composition for pure components. So both these terms are 0. And what we'll get is x1 double ln a1 by double x1 is equal to x2 double ln a2 by double x2. This is another form of Gibbs Unit equation. So what you get is essentially activity or activity coefficient. All these are dependent on each other. You've seen this for fugacity. You've seen this for chemical potential. All these are independent, not independent of each other. They are all dependent on each other. For one component, if it changes, it has to change for second component also. ठीक है? Any questions on equation 14? Okay, let's put out then let's move forward. You know the Lewis Randall rule says Fi bar is equal to xi into Fi. For non-ideal solutions, we have defined Fi bar is equal to gamma I xi Fi, right? We introduced the concept of activity coefficient for non-ideality. We can write gamma I is equal to Fi bar by xi into Fi. And we know that Fi bar by Fi is nothing but activity. So it is Ai by xi. That means you can write Ai is equal to gamma I into xi. So if we substitute equation 15 in 14, this equation, what we'll get is x1 double ln gamma 1 x1 instead of activity. We get activity coefficient into composition by double x1 is equal to x2 double ln gamma 2 x2 by double x2. And this is nothing but x1 double ln gamma 1 by double x1 plus x1 double ln x1 by double x1, breaking it, expanding this thing, is equal to x2 double ln gamma 2 by double x2 plus x2 double ln x2 by double x2. Okay? And if we take this term, x1 double ln x1 by double x1 is equal to x1, and if you expand this is nothing but 1 upon x1 double x1 by double x1, right? So this is 1 and this cancels out, so this is 1. Similarly, x2 double ln x2 by double x2 is equal to nothing but x2 into, if we expand this is 1 upon x2 double x2 by double x2, this is 1, this cancels out and you get equal to 1. So equation 16 will become, this 1 and this 1 will cancel out, sorry, this 1 and this 1 will cancel out, and what you'll get is this term and this term. What you get is x1 double ln x1 by double x1, double ln gamma 1 by double x1 is equal to x2 double ln gamma 2 by double x2. This is another form of Gibbs equation. This is for activity coefficient. We have seen the activity coefficient, fugacity, activity, chemical potential. They are all similar equations because they are all related to each other. Any questions, doubts on equation 17? Yes, no, don't know. Can you hear me?
Yes, sir.
Okay. So this simple derivation है, इसमें ज़्यादा कुछ नहीं है, but you can get some question on derived Gibbs equation, and we'll use this in some of future derivations also. ठीक है. So this was simple derivation. Let's go to the next topic, which is property changes of mixing. Okay. So we have defined ideal solutions as, for ideal solutions we defined V equal to summation of xi into Vi, pure component molar volume. This is nothing but Avogadro's law, right? You've seen this before. So if you apply similar equation for all thermodynamic properties, if you say okay, we can use it for all thermodynamic properties. Again, see, always expanding, right? We are going from ideal to non-ideal, right? We are going from simple to complex things. So we are saying assuming, let's say assume that okay, we can apply a similar equation for all thermodynamic properties. Then what happens? Is it applicable? That's what we are going to look at. But it is observed that equation 2 is not true even for ideal solutions if we consider entropy or Gibbs energy. बाकी सबके लिए होता है, but entropy के लिए observations, you hypothesize something. Okay, this is your hypothesis that okay, we can use similar equation for all properties, and then you make some measurements. Measurements क्या तो नहीं, this is not applicable for entropy and Gibbs energy. बाकी के लिए applicable है. So these are exceptions then. And then we find out कि if there are exceptions, how do we handle exceptions? So that's what we are going to do that. So for non-ideal solutions, apply correction term. जैसे हमने gamma किया, right? We have to introduce gamma activity coefficient to correct for non-ideality, right? Here also we are saying the same thing, right? अगर non-ideal है तो क्या effect है उसका? How do you handle that non-ideality? So we apply a correction term here, which is called delta m, which is called property change of mixing. जैसे हमने देखा था मिथेनॉल वाटर में प्रॉपर्टी चेंज होता है, राइट? मोलर वॉल्यूम और मोलर वॉल्यूम ऑफ सॉल्यूशन इज नॉट इक्वल टू सम ऑफ मोलर वॉल्यूम ऑफ कंपोनेंट्स, राइट? सो यहाँ पर डेल्टा एम क्या होगा, which can help us find out the molar volume of solution. So therefore use this equation for thermodynamic property of ideal or real solution. We can use for all. M is equal to summation of xi mi plus delta m. Now this is a correction for non-ideality. The first part is for ideal solutions. Non-ideal हुआ तो क्या होगा? कुछ तो होगा. Delta m can be positive or negative. We've seen that, right? In some cases it was positive, some cases it was negative. So delta m is difference in property of solution of the solution m and sum of property of pure components, right? So if I take delta m on this side, on this side, take this on the other side, I get m minus summation of xi mi. Now that is how we define our delta m. ठीक है? Understand questions on equation 4. किसी को डाउट है तो पूछ सकता है.
MI को क्या डोनेट, मतलब MI क्या है?
MI is pure component property. पहले देखा था ना हमने यहाँ पर. We said that Avogadro's law is what? V is equal to summation of xi vi. Vi is molar volume of pure component. Ideal solution को बोला था ना. There is no volume change on mixing. That's what Avogadro's law was. हमने देखा था पहले. So we are saying कि अगर similar model हमने apply किया for all thermodynamic properties, it will be Mi is equal to summation of xi mi, where Mi is pure component property and M is solution property. But that is not applicable for all solutions.
Okay, sir, I got it.
Right? It's not applicable for all solutions. And then we define delta M. क्या effect होगा? Non-ideal होगा तो क्या होगा? And that's how we define. Right? Plus delta M. M is equal to summation of xi mi. ये pure, ये ideal solution के लिए है और delta M. Non-ideal solution क्या हो जाएगा? Delta M equal to 0 हो जाएगा. But for real solution, delta M will be either positive or negative. So we define delta M is equal to nothing but solution property M minus ideal solution में क्या होता है? Summation of xi mi. ठीक है? समझ में आया? Just like we had defined some residual property.
Yes, sir.
Residual property define किया था ना हमने. वैसे यहाँ पर saying we are defining property changes of mixing. Mixing के बाद क्या change होता है, कैसे change होता है, we are defining that. Right? So if you write this equation for molar volume, equation ये वाला, instead of general property M, we say volume लिया तो V is equal to summation of xi vi plus delta V. The delta V is volume change of mixing. Now this delta V या delta M is equal to 0 for ideal solution. जैसे हमने देखा gamma is equal to 1 for ideal solutions, right? We define something for non-ideality, saying ये effect है non-ideality का. But what happens when the solution behaves ideally? Just like gamma equal to 1 हो जाता है वैसे यहाँ पर डेल्टा m इक्वल टू 0 हो जाएगा, डेल्टा v इक्वल टू 0 हो जाएगा फॉर आइडियल सॉल्यूशंस. So we are handling both now. We are handling ideal solution as well as non-ideal solutions by the same equation. One thing is value of delta v or delta m will change depending on type of solution. ठीक है? Any questions? Conceptually समझ में आ रहा है? Property change of mixing. Any doubts? नहीं है, ठीक है. There are no doubts. Let's proceed further. Okay. So you can write delta m is equal to m minus summation xi mi 0. यहाँ पर 0 डाला because we are saying कि pure component के लिए molar property is saying pure solution का standard state है, right? We always take pure solution, pure solvent as standard state. So we are saying mi 0 डाला इसमें. If component exists in pure form in the same state as solution at same temperature and pressure, then mi 0 is equal to mi. We just replace mi with mi 0 because that's the standard state we define, right? So for Vi, for volume, Vi 0 equal to Vi, and then delta V यहाँ पर Vi 0 रहना चाहिए, x minus x, V minus summation of xi into Vi 0. Because standard state is pure component at same temperature and pressure. So what we know is mi is equal to summation of xi mi bar, right? We हमने पहले define किया था जब हमने partial molar volume निकाला था, right? Where mi bar is partial molar property and m is solution property. This is for real solutions, right? And now we have defined m is equal to summation of xi mi 0 plus delta m for non-ideal solutions or real solutions, right? So this should, left hand side of 9 and 10 is same m, right hand side has to be same or equal. So if we compare 9 and 10, what we'll get is delta m is equal to, ये दोनों इक्वेट कर दिया राइट हैंड साइड दोनों का, what we get is summation of xi mi bar minus ये इधर आ गया summation of xi mi 0, and that is equal to nothing but delta m is equal to summation of xi into bracket mi bar minus mi 0, where mi bar is nothing but partial molar property of I in solution, this one, minus partial molar property or molar property on standard state of pure component mi 0. So this is our what you call property change on mixing. अगर mixing किया हमने दो component और solution बनाया तो how will the property change? Or it can be volume change, it can be free energy change, it can be entropy change, any thermodynamic property. Questions on equation 11?
सर एक बार रिपीट करो ना थोड़ा, 11 पे फिर से पूछो थोड़ा सा.
Okay. ये समझ में आया था. You got this. Delta m is equal to m minus summation of xi mi 0. Equation 6. Because we said that mi 0 is the property of pure component in standard state, right? Mi 0 is equal to mi. That's how we define standard state. And similarly we define for volume also. Now let us look at this one. ये हमने पहले define किया था long back. Property of solution m is equal to nothing but summation of xi into mi bar. The mi bar is nothing but partial molar property of each component. Component I. This for real solutions. ये हमारा definition था, right? जो हमने निकाला था शुरू में दिया था, right? And now we have defined another way of finding m is nothing but summation of xi mi 0 plus delta m by introducing this property change of mixing. This for ideal solution, this is non-ideal defect. और यहाँ पर already non-ideal defect built in है because we are taking partial molar property in equation 9 and यहाँ पर pure component property लिया equation 10 में. तो equation 9 और 10 का डिफरेंस समझ में आया?
Yes, sir.
Equation 9 and 10 का डिफरेंस समझ में आया तो then it's easy. Then you just compare equation 9 and 10. Left hand side is same m for both the equations, so right hand side has to be equal, right? So summation of xi mi bar is equal to summation of xi mi0 plus delta m. तो डेल्टा m एक साइड में रखेंगे और इसको इधर लेके आएंगे, तो व्हाट इज डेल्टा m इज इक्वल टू समेशन ऑफ xi mi bar minus summation of xi mi0. And if you take xi common, what you get is delta m is equal to summation of xi into bracket mi bar minus mi0. Now this mi bar is nothing but partial molar property. That means it is property of component I in solution, mi bar, and mi0 is nothing but pure component property, right? So अगर ये different रहेगा, mi bar is different from mi0, तो ये डेल्टा m रहेगा कुछ नंबर. अगर ये सेम रहेगा, हमने देखा था आइडियल सॉल्यूशन के लिए पार्शियल मोलर प्रॉपर्टी इज इक्वल टू मोलर प्रॉपर्टी, राइट? आइडियल सॉल्यूशन के लिए डेल्टा m विल बी इक्वल टू 0.
सर जो डेल्टा है वो पॉजिटिव और नेगेटिव दोनों हो सकता है ना?
दोनों भी हो सकता है. एनीथिंग, इट कैन बी एनीथिंग, पॉजिटिव और नेगेटिव, डिपेंडिंग ऑन सॉल्यूशन. ठीक है?
Yes, sir. Yes,
Okay.
sir.
So now if you use this equation 11 for volume, delta V is equal to summation of xi into Vi bar minus Vi0, right? And if you use it for Gibbs free energy, delta G is equal to summation of xi into Vi bar minus Gi0. We can write for any property. You can take entropy, we can take enthalpy, we can take any property and write this equation, this general equation for any thermodynamic property. M is any thermodynamic property. We can substitute M for any property, and we get equations for different properties. और volume or property change of mixing क्या होगा? How does Gibbs free energy change when we mix two components and make a solution? How does volume change when we mix two components and make a solution? We can write for anything. Entropy के लिए लिख सकते हैं हम, enthalpy के लिए लिख सकते हैं, सबके लिख सकते हैं. ठीक है? Equation 12 and 13. Okay. So now we are going to correlate this with activity. Okay. Because ultimately हमारा non-ideality का relation है gamma, right? So you have to find out some way to correlate it, right? So free energy change of mixing is delta G, right? हमने define किया dg is equal to RT dln f. This is our definition of figurativity, right? So if you integrate this from, say, if you go from pure component Gi0 to solution, that means we are saying taking pure component and making solution. तो G का integrate dg from pure component Gi0 to Gi bar. This is solution का property. That we get RT integral dln f from Fi0 pure component to solution property Fi bar. What we'll get is Gi bar minus Gi0 is equal to RT ln Fi bar by Fi0, right? And this Fi bar by Fi0 is nothing but activity. So RT ln AI. ठीक है, equation 14.
Yes, sir.
Okay. So this is nothing but delta G. You know delta G is equal to summation of xi Gi bar minus Gi0, right? हमने देखा था यहाँ पर, right? Delta G is equal to summation of xi into Gi bar minus Gi0, equation 13, right? वही लिखा हमने यहाँ पर. So if you substitute 14 in 15, ये जो हमारा equation है, if you substitute for Gi bar minus Gi0 in this equation, what will get is delta G is equal to summation of xi into इसकी जगह पे RT ln AI. ठीक है, we are substituting this equation for Gi bar minus Gi0 into equation 15. So what you get is, if you divide this RT इधर constant निकाल दिया बाहर, delta G by RT is equal to summation of xi into ln of AI. So now we have a relation between Gibbs free energy change क्या होता है, कैसे change होता है, with activity. This because this activity is related to gamma activity coefficient. ठीक है, equation 16.
Yes, sir.
Okay. So similarly, we'll see for all properties now. Now we have proper change effect of what you call how's the property change of how does free energy change on mixing related to AI. Similarly, we get for volume change. So effect of pressure on partial molar free energy हमने निकाला था पहले long back, right? Which is delta GI bar by delta P at constant dava GI bar by dava P at constant temperature and X composition same constant है is equal to VI bar. And for pure substance, we can write dava GI0 by dava P at constant temperature is equal to VI0 along these lines, where VI bar is partial molar volume of I and VI0 is molar volume of I in standard state, that is pure component. If you take delta V are defined summation of xi into VI bar minus VI0. यहाँ पर देखा था हमने, right? So we are writing the same thing here. Right? So now we substitute 17 and 18. VI bar के लिए 17 है और VI0 के लिए 18 है. ये substitute करेंगे इसमें equation 19 में. What we'll get is delta V is equal to summation of xi into VI bar is nothing but dava GI bar by dava P at constant temperature composition minus dava GI0 by dava P at constant temperature and composition है नहीं because it is pure component. So what we'll get is summation of xi into dava GI bar minus GI0 by dava P at constant temperature and composition. And we know that GI bar minus GI0 is RT ln AI. Equation 14 हमने ऊपर देखा था. So we substitute in this one, equation 20, what we'll get is delta V is equal to summation of xi into this is nothing but RT और ये dava ln AI by dava P at constant temperature में x हो जाएगा. ठीक है, यहाँ पर हमने equation 14 substitute किया. तो RT कॉमन है, इंडिपेंडेंट ऑफ प्रेशर है, तो बाहर आ गया और ये dava ln AI by dava P at constant temperature and composition हो गया. So multiply both the sides by P, left hand side, right hand side. So what is P into delta V is equal to RT summation of xi, RT कॉमन निकाला बाहर कांस्टेंट है, into summation xi P dava ln AI by dava P at constant temperature x. So if you combine dP by P, what is dP by P?
DLNP.
DLNP, right? So what you get is P delta V, RT इधर आ गया लेफ्ट हैंड साइड में डिवाइड कर दिया, is equal to summation of xi into dava ln AI by dava ln P at constant temperature and composition. So now we have a relation between delta V and again activity. ठीक है, इक्वेशन 22 समझा? Any doubts on equation 22?
सर वहां पे हमने वो जो एक्टिविटी करता है प्रेशर पे डिपेंडेंस, वो इक्वेशन भी डाल सकते थे ना, इफेक्ट ऑफ प्रेशर ऑन एक्टिविटी.
ये तो लिया है ना. अच्छा वो नहीं, लेकिन एक्टिविटी कहाँ से आएगा, कहाँ से आएगा? We have this is delta V is equal to summation of xi VI bar minus VI0, right? So we have to take VI bar and VI0 का equation ना. Okay, you are saying activity directly लेने का कर सकते थे हम. Yeah, we could have done that directly. Yes, you are right. कर सकते थे. Yeah, there is another possibility. Yes, we could have done that. Directly मिल जाता था हमको ये equation. Yeah, you are right. ठीक है. Good suggestion. You can do it. It's derivation. You can do it anyway. ठीक है, कोई क्वेश्चन है क्वेश्चन 22 पे? ओके, नहीं है तो लेट्स मूव फॉरवर्ड. एंथैल्पी चेंज ऑफ मिक्सिंग. सिमिलरली वी कैन डू ऑल प्रॉपर्टीज, राइट? सो डेल्टा एच का लिया हमने इक्वेशन यहाँ पर, वी हैव दैट गिब्स हेल्महोल्ट्ज इक्वेशन dou gi bar by t dou t at constant pressure x is equal to minus hi bar by t square. Similarly, for pure component, you can write dou gi 0 by dou t at constant pressure x is equal to minus hi 0 by t square. Enthalpy of mixing is enthalpy change of mixing is enthalpy change आना चाहिए यहाँ पर. Delta H is equal to summation of xi into hi bar minus hi 0. And if we substitute this equation and this equation here in equation 25, what we'll get is delta H is equal to minus t square. ये माइनस टी स्क्वायर आएगा hi के लिए, इधर से टी स्क्वायर आ जाएगा, ये इधर से टी स्क्वायर आ जाएगा, इंटू समेशन ऑफ xi इंटू dou t gi बार माइनस gi 0 बाय t. यही है gi बार minus gi 0 by t at constant pressure and composition. And we know that gi bar minus gi 0 is RT ln AI, and we can write delta H is equal to minus, substitute किया हमने यहाँ पर equation 27 in 26. So what you'll get is minus RT square summation of xi ln AI by dou t at constant pressure and composition. Right? ये एक टी यहाँ पर लिया हमने अंदर, डेल्टा एच इज इक्वल टू माइनस आर टी समेशन एक्स आई इंटू टी ए अंदर लिया, डबा एल एन ए बाय डबा टी एट कांस्टेंट प्रेशर एक्स, एंड वी कंबाइन टी एंड डबा टी, व्हाट गेट इज डेल्टा एच बाय आर टी इधर लिया हमने डिवाइड के इक्वल टू माइनस समेशन ऑफ एक्स आई डबा एल एन ए बाय डबा एल एन टी एट कांस्टेंट प्रेशर एंड कंपोजिशन. ठीक है. वी कैन डन फॉर एक्टिविटी ऑल्सो डायरेक्टली, जैसे देवेंद्र ने बोला, किसने बोला था?
हाँ सर.
ये भी कर सकते थे, इसमें भी कर सकते थे हम. वो इक्वेशन जो है हमारा एक्टिविटी का, वो इक्वेशन डायरेक्टली कर सकते थे यहाँ पर. इंस्टेड ऑफ स्टार्टिंग विद दिस वन, वी कुड स्टार्ट विद एक्टिविटी. we'll get the same equation. ठीक है. लेट्स सी एंट्रोपी के लिए, एंट्रोपी चेंज ऑफ मिक्सिंग. dou gi bar by dou t at constant pressure x is equal to minus si bar, partial molar entropy. And for pure component, we can write this equation 30, dou gi 0 by dou t at constant pressure x minus si 0. Right? This is partial molar entropy si bar, and si 0 is molar entropy of pure component. And we know entropy of mixing is delta S summation of xi minus xi into bracket si bar minus si 0 by definition. So if we substitute equation 29 and 30, what you'll get is delta S is equal to minus, because it is minus here, यहाँ पर माइनस है, यहाँ भी माइनस है, तो ये माइनस हो जाएगा, समेशन एक्स आई इंटू डबा जी आई बार माइनस जी आई 0 बाय डबा टी एट कॉन्स्टेंट प्रेशर एक्स. एंड वी नो दैट जी आई बार माइनस जी आई 0 is RT ln AI. If you substitute in equation 33, you'll get delta S is equal to minus summation of xi into r daba t ln AI. T we cannot take outside because its derivative with respect to t है, तो daba t ln AI by daba t at constant pressure and x. हमने ये इसको एक्सपांड किया, माइनस आर बाहर निकाला, समेशन एक्स आई टी इंटू डबा एल एन ए बाय डबा टी, फर्स्ट फंक्शन इंटू डेरिवेटिव सेकंड प्लस सेकंड फंक्शन डेरिवेटिव फर्स्ट, राइट, प्लस एल एन ए आई डबा टी बाय डबा टी, दिस इज 1, और ये एल एन टी हो जाएगा. तो व्हाट इज इज डबा एस और डेल्टा एस बाय आर इधर लिया, माइनस इक्वल टू माइनस समेशन ऑफ एक्स आई डबा एल एन ए आई बाय डबा एल एन टी माइनस अगेन ये जो टर्म है एक्स आई समेशन ऑफ एक्स आई इंटू एल एन ए आई. दिस इज इक्वेशन यू गेट फॉर delta S. Any questions on equation 34? यहाँ भी एक्टिविटी से कर सकते थे हम. Instead of starting from G, we could start with the activity just like he said. We should get the same equation. So we'll stop here because we're going to look at how does this simplify. Now all this is for non-ideal solutions, right? That is real solutions के लिए क्या है? How does delta S change? How does delta H change? How does delta G change? All these things we have seen is common or general equations for real solutions or non-ideal solutions. What happens now if they are ideal solutions? We'll see next time. Simplify क्या होता है? तो बाद में करेंगे हम, next time करेंगे. ठीक है? Any doubts, questions on properties of mixing? Yes, no, don't know, समझा नहीं समझा.
समझा सर.
Okay. I have done all these things in OneNote. I don't know if I can share this with you directly OneNote में. नहीं तो मैं PDF डाउनलोड करके आपसे शेयर कर दूंगा. Okay. So if you have no questions, then we stop the recording.